at 1:15. So we have now 3 talks. The first talk will be on engineering quantum systems by William Oliver from MIT.
Okay.
Labs, I guess.
Yeah, both MIT, Lincoln Lab and MIT.
Okay. Please, William.
Thank you, Hartman. And thank you to the organizers, and in particular Irfan, for organizing this 3-day conference and also honorarium for John Clark. It's really been a pleasure to participate. And I'd like to tell you today about our work at both Lincoln Laboratory and MIT on engineering quantum systems. So just as, introduction, of course, there are many applications of a quantum computer, but it can be boiled down to 2 basic ones, if you'll allow me to do that. One, of course, is a universal quantum computer, such as what you see here, the Shor's algorithm for prime number factorization. And these are generally gate-based quantum computers, fault-tolerant. And a few applications are decryption, database searching, and of course, what is of interest today is quantum simulation. And there it can be either analog or digital, or in fact, some combination of both. And I'll talk a bit about that in more detail. We just heard a talk also about quantum annealing, which is another activity that we're working on at MIT. And these applications are usually some type of constrained optimization problem, such as transport optimization, satellite tasking, pattern recognition. And in this case, it's unknown yet if a quantum speedup exists with this approach, but we feel it's very important to pursue because if there is some advantage to be had, the application pull is so strong that we want to be able to realize it. And of course, on the left, I didn't mention it, but if we can build a universal quantum computer, then okay, then we know that we can do fantastic things. And in terms of a gate-based quantum information processor, if we look at architecturally how would we build such an object, okay, this is quite high level, but we have 5 layers here, and this is based on Cody Jones' work a few years back when he was at Stanford. At the high level, at layer 5 is the application and the human-computer interface inputting the problem into the computer that you have. And at the bottom are these physical qubits, the hardware that we'll use to implement the algorithm. And in between, you see layers such as passive error suppression, active error correction, and the logical controller. And really, these are there to implement fault tolerance. And because we know that these physical qubits are faulty, and even though we've made great strides, right? Error rates are now 1 part in 10 to the 4 or 10 to the 5. If you compare with, say, conventional classical computers that we're using today, the error rate is something like 1 part in 10 to the 20. And of course, we'll continue to make improvements to these faulty qubits, but that is a huge gap to fill. And so in the meantime, we need something like this, which is this virtuous cycle of error detection, recording, maybe even mitigation, and then logical operations and error correction on the other side. And this is very much worthwhile to pursue. But in parallel with this, I think that we want to also do quantum simulation demonstrations on smaller systems of, say, 10 to 100 qubits. Now, of course, to realize a quantum computer, there are many modalities, and I acknowledge right off that this is not entirely up to date. This is maybe from around 2015. And the axes here are the fidelity, if it's been measured. If it hadn't been measured by these systems, then what's here is essentially a proxy of coherence time to gate times. How many gates can I implement within a coherence time? And on this axis is the speed, the gate speed. And solid circles mean, okay, more or less the DiVincenzo criteria have been demonstrated. And the open circles means that they're still working on it. Okay. This is roughly a threshold, the lowest threshold for error correction that we know in the surface code, roughly speaking. Okay, and of course the upper right corner is where the best performance is. There are 2 modalities that we're working on at Lincoln Laboratory, and hopefully it'll become clear why we've picked these 2. One is trapped ion qubits, where the gate time is 10 to 100 microseconds typically, and also the readout time. Coherence time's very long, 1 to 50 seconds, maybe even longer. And the other are superconducting qubits, shown here, where the gate time is 10 nanoseconds, so very, very fast. And the coherence times are about 100 microseconds. And the effort that we have at Lincoln, then, is to improve trapped ion qubits by making them faster, and in particular reading them out more quickly with higher fidelity. And on the superconducting qubit side, it's really to make them have higher fidelity in all aspects, both the gates as well as the readout. Now let me start with superconducting qubits. We like them because these are manufactured or designed artificial atoms. We fabricate them using planar fabrication processes, the same that we use for CMOS, and in fact in the same facility, on the same tools. They're controlled in the RF or the microwave. They're fast, and this is a real advantage, 100 megahertz gate operations. You know, it's an advantage because, let's say with a gate-based computer, we're very happy that something that would take the age of the universe doesn't anymore. That's fantastic. But if it takes us, for example, a day on a superconducting quantum computer to do a task, and it's 1,000 times faster than an ion-trapped quantum computer, it will take 1,000 days, which is about 3 years. And so the human timescale matters, that prefactor matters. And so that's why we are trying to make ion traps faster. And this Moore's law type behavior for coherence times, that the coherence times have increased more than 5 orders of magnitude in the past 10 or 15 years, is also something that motivates us. And the blue dots in here are contributions that we've made to this trend at MIT and Lincoln Laboratory. But of course, it's been an effort by groups worldwide. A few highlights. I won't dwell on this for too long, but we span, I would say, from basic, more fundamental physics, atomic physics with artificial atoms. For example, here is a demonstration of cooling of our artificial atom or qubit, superconducting qubit, to temperatures of 3 millikelvin, even colder than the dilution refrigerator, borrowing ideas from atomic physics. A number of experiments like this in Landau-Zener transitions. Noise spectroscopy is an area that we've contributed to strongly, and in particular showing that this 1/f flux noise not only causes dephasing in a classical sense, but it can also cause relaxation in these superconducting qubits. We've done quite a bit of work on high fidelity control. We're at about 3 nines right now, both in terms of randomized benchmarking and dynamical decoupling. And something I will talk about a bit later due to the topic is a quantum simulation of very simple quantum simulation of a universal conductance fluctuations. And I'll return to this in a moment. Now on the trapped ion qubit side, we're working in several areas, and we like them because these are, the electronic states of ionized atoms, as we heard about in the public lecture on Monday. The traps are in the RF, but the control here generally is optical in the case that we're doing. Coupling is via Coulomb interaction, and the gate times are approximately 100 kilohertz. And our focus at Lincoln is both, as I mentioned, to speed up this time, or this rate, but also to develop scalable technologies for quantum control of trapped ions. And I'll talk about these in more detail also. A few highlights. Again, we won't be able to talk about all of these, but the high rate of ion loading, this is something we pioneered at Lincoln Laboratory, where we use a magneto-optical trap to first cool the atoms before we blow them over with a laser, push them over to the trap, ionize them en route, and then trap them on the chip. This is something that works very, very well, and I'll show some examples. 2D arrays of ions, we've now demonstrated this. I'll show some pictures. We've studied the motional decoherence, or this anomalous heating effect that occurs in ion traps. And this has been done by ion milling as well as cooling the trap to 4 Kelvin. And this is important because part of speeding these ions up is bringing them closer to the trap surface. And as we bring them closer, of course, we may become more impacted by this, whatever mechanism is heating these up. Okay, and then I will show more on cryogenic CMOS and integrated photonics as we try to make scalable engineered systems. And so this is our quantum information science group at MIT Lincoln Laboratory. It comprises both high-performance quantum computing as well as high-performance classical computing, superconducting qubits and trapped ions, as I mentioned. On the classical side, integrated photonics, which it's clear how that impacts trapped ions. Superconducting SFQ, which is a digital classical technology, computing technology based on Josephson junctions, as well as cryogenic CMOS and 3D integration, which impacts both of these. And the work is performed at Lincoln Laboratory in the Quantum Information and Integrated Nanosystems group, as well as at the MIT campus. I'm also a professor of practice in the physics department, and my group there is Engineering Quantum Systems, or EQS. And we also collaborate with Ike Chuang and Rajiv Ram on the ion trap side. Okay, so with that introduction, let me now talk about some of the systems integration for extensibility on both superconducting qubits and trapped ions. And then we'll do some science and talk about quantum simulation of universal conductance fluctuations. So if we think about the quantum to classical interface as it looks today, probably you've seen a lab like this. This is one of our dilution refrigerators, and we're very happy. We can put 12 devices in there, and measure them all, okay, and there's some switches to route the signals. And in ion traps, this is an optical table with lots of elements. But clearly, this is good for few qubit experiments, but this is not extensible. And we need to find approaches to make this look more like a quantum computer that we envision. So on the superconducting side, as part of the IARPA Quantum Enhanced Optimization Program, we are working very heavily on 3D integration. And the reason to do this is really a fewfold. One is we need a high interconnect density. If you make a 2D array of qubits, we can't bring the wires in entirely from the side. I think that's clear. That we do need to use the third dimension. Another reason to do it, though, is that the fabrication processes that give us very high coherence, these 100 microsecond qubits, are very different than the fabrication processes that give us multi-layer interconnect wafers. And maybe someday we'll figure out how to do it all monolithically in one process. And we're thinking about that. But we don't want to wait for that day. And so what we can do is, in fact, make what we call a 3-stack, where we fabricate the interconnect and readout layer independently from the qubit layer. And then we connect them together with what's called an interposer, which has through silicon vias that connect the wiring that you have from the interconnect plane up to the qubit plane. So this is what it looks like. They start out separate, and then we eventually will bump bond them together. And again, this improves the overall performance by maintaining this process independence. We don't have to fabricate this monolithically. So on the qubit layer, we've recently demonstrated a capacitively shunted flux qubit with T1s around 50 microseconds and T2s with an echo approaching 100 microseconds. This is a capacitively shunted flux qubit. Using 2 of those and designing for the annealing application, we've demonstrated ZZ coupling between qubit A and qubit B using a third object which looks a lot like a qubit, but in this case, it's a coupler. And by biasing the coupler, we can turn the coupling off or on. And we now have this avoided crossing. This 2J is in excess of 1 gigahertz at this point. And how small can it be? Okay, it becomes a limit of how well you can resolve these levels. But it's essentially 0. Okay, so that's the qubit layer. Now, this interposer layer, which brings the signals from up to the qubit layer, this requires TSVs, or through silicon vias. And what we're showing here are just some SEMs. High aspect ratio, so the depth that we're etching holes into the silicon wafer is 160 microns, but the diameter here is only 4 microns wide. And what you see here is titanium nitride, which is filled in all the way down to the bottom, and it's superconducting. And we can even make things that look like shielded coaxes. You can have a wire in the middle with a guard ring around the outside, circular or in a raceway. And this is just to give some ideas of the types of things that we are doing. And then at the bottom, we need a way to get wires into the center or to the location within this 2-dimensional array where we can bring them up to the surface. And to do that, we need a multi-layer process. And to do this, we use niobium, a niobium process. Here you see 8 metal layers. It's a bit dated. We have 10 metal layers now. And we use this not just for interconnects, but it has active Josephson junctions, as you see here. And so it's part of this digital classical superconducting logic family called SFQ, single flux quantum. And so we've demonstrated in excess of 800,000 Josephson junction circuits now. The density is in excess of 1 million junctions per square centimeter. That density is comparable to roughly the first Pentium that came out in the late 90s. What you see here is a 500 nanometer junction, a larger junction here, vias, etc. And so we use this for connecting wiring from the outside in. We also used it in collaboration with Irfan here at Berkeley to make the traveling wave parametric amplifiers, which some of you may be familiar with. Essentially, this is a 50 ohm transmission line where the L's and C's in a ladder formation like this, choosing the right value of L and C, can make a 50 ohm impedance. But the nonlinearity is gained by replacing the inductors with Josephson junctions. So it's a distributed nonlinearity over about 2,000 junctions. And once in a while, you'll see a little resonator here. This is to do phase matching. Due to the nonlinearity, the pump will travel at a different velocity than the signal we're trying to amplify. And so by putting a resonating feature in there, we can rephase the pump and the signal periodically along this transmission line. Here's a picture of the chip, 5 by 5 millimeters, and an SEM of some of the capacitors, inductors, Josephson junctions, and this resonance feature. So the very nice thing about this, it has very high gain, 20 to 25 dB gain, but the real advantage is it's over a very large bandwidth, 4.5 gigahertz. It's in many ways comparable to the Josephson parametric amplifiers that Irfan and others have been making for many years, but those had a fairly narrow bandwidth. Now, it was tunable, but the instantaneous bandwidth was maybe 10 to 50 megahertz, and you could move it around. But this one is just broadband right from the get-go. And it's nearly quantum limited. The quantum efficiency is maybe 50, 60%. So it's a very good amplifier. And, of course, the utility of it is that we can use it to read out multiple qubits through frequency multiplexing. And so, again, to emphasize this interconnect and wiring layer, these traveling wave amplifiers are made with that process. So they can be co-located with the qubits that we are routing the signals to. So, of course, this 3-stack now has to be assembled and put together. And to do that, we need to use a bump bonding type process. And so the idea here is what we've demonstrated is flip chip. So you have 2 chips. One of them gets flipped over. And then using a thermal compression bonding technique and indium bump bonds, we connect them together. This is what it looks like once it's been bump bonded. So the black chip is on the bottom and the gray one is on top. And this was done using annealing qubits where the coherence time or the T1 time was about 20 microseconds as a bare chip. And then we flip it over and we still get about 20 microseconds. So the point being that this process didn't lower the coherence times to the extent that we've measured it. And we've demonstrated these 4 basic building blocks. As you see here, just putting these 2 chips in proximity to one another, did we harm the coherence? And the answer is no. But we've also demonstrated biasing the qubit electrical conduction through these bumps. We've capacitively coupled between the 2 chips. So the readout resonator was on the interposer, reading out a qubit on the qubit chip. And then, in fact, we've also flux biased the qubit chip, the qubit on the qubit chip with an antenna on the interposer. So this is somehow a basis of different things you might want to use flip chipping for. Now, in addition to the superconducting digital logic, we also have an effort in cryogenic CMOS. And what I can share with you today, we've been working on this for more than 10 years. What I'd like to say is our application of signal routing. So the cryogenic CMOS that we've designed, its one feature is that it's designed to work at 4 Kelvin. So we're not taking room temperature CMOS and cooling it down. We're taking CMOS, designing it to work optimally at 4 Kelvin. And in fact, it doesn't work that well at room temperature. Okay. So one application you might imagine is signal routing with these. And so what you see here are 2 DIM boards. These 2 DIM boards have devices that we want to measure. In this case, just Josephson junctions. And there are a lot of them. Let's say 151 Josephson junctions on these 14 chips. And a standard approach to do a 4-wire measurement would require roughly 14 by 24 wires. A lot of wires. You're just doing 1-to-1 wiring on the junctions and doing 4-wire measurements. With the CMOS, it only requires 24 wires. 4 wires to do the measurement and 20 wires to tell the CMOS where to route the signals. Okay. And so this is what it looks like when we put it in our dilution refrigerator at 20 millikelvin. And here is an example of some Josephson junction IV traces that we've taken at 20 millikelvin using the cryogenic CMOS to route the signals. Okay, and now let me tell a bit about trapped ions. There are a number of integration approaches that we've done, and in the interest of time, I'm going to just not read this and just rather show the results. So one is this loading on demand that I mentioned. So this is a 2D array, and we use a magneto-optical trap to cool the ions, or the atoms, and then we push them and ionize them. And you can see here what's happening is we're loading them selectively in the different spots. And one should appear here. Yeah. And so the loading time is very fast, milliseconds, and then the lifetime, they last for hours. Okay. Now, of course, when we do coupling, we end up heating up the ions. And what we need to do is, in fact, have another species. So our ion is strontium, but we can use another species, calcium, to essentially remove entropy. So it takes some of the motional vibration out of the data qubit, which is a strontium, and puts it into the calcium. And so this is, we co-trap a second sympathetic ion, as it's called. And we've demonstrated that. And we show here that we can control the strontium even in the presence of the calcium. Okay? Now, the third thing is we need to integrate the photonics on chip. And so we've done that. And what we have here are essentially silicon nitride waveguides on quartz silicon dioxide buffer layers. And they're grading coupled. And what you can see here is we have 5 ions trapped, and we are intentionally only using the integrated photonics to control the middle one. So we have very good isolation with the neighbors. And all of these, of course, are controlled. And you can see here, you know, oscillations doing Rabi. Okay. Now, then we're also integrating the electrical control. And what you see here is CMOS and DACs and amps, which are generating the electrode voltages, which are used to trap the ions. These are integrated in. And also, we're now integrating, we are doing this, don't have a demonstration to show, where we're putting Geiger mode avalanche photodetectors, also integrated with the ion traps to do readout. And as with the superconducting qubits, this all gets bonded together. And so here's take a break, okay? Here's a little movie of what this would look like, we imagine, how an ion trap would operate. And okay, the superconducting qubits are similar. The idea is that you have a qubit here, and then you can control it with these grading couplings. And then you move the ions around through the integrated electronics, controlling the gates. And this, of course, is showing an example of nearest neighbor couplings as you might do on a surface code. And the superconductors look similar. The qubits just don't move. And in the remaining very few minutes that I have, let me talk about quantum simulation. And so universal conductance fluctuations, okay, basically it's based on coherent backscattering. So radiation is reflected in disordered medium, and it gives enhanced scattering in the backwards direction. And this is due to constructive interference and time reversal symmetry. It's observed in condensed matter systems. It also is a concern for people who are designing radars, as the scattered waves in the clouds can exhibit a similar effect. Okay. Now, we see this in condensed matter as a decrease in conductance. And what you're seeing here are the scatterers and waves going clockwise and counterclockwise. And you can break this time reversal symmetry, in this case, with a magnetic field. And this leads to some interesting consequences. One is weak localization, so a decreased mean conductance observed in the system. And also, so that's a first order statistic, the average conductance. And then in addition, there can be a second order statistic, or the fluctuations in that conductance. And these are called the universal conductance fluctuations as a function of this time reversal breaking symmetry parameter. Here it's a magnetic field. Okay. Okay, so can we do this with a driven two-level system, something like this? So very early on, one of the first experiments I did with a superconducting qubit was to look at Landau-Zener transitions at an avoided crossing from our qubit. So the two levels, so the ground and excited state. And the idea was to start at a point and drive the qubit sinusoidally back and forth. And rather than what we usually think of as driving a resonant transition from ground to excited state, here we can think of this as an interferometer. And this avoided crossing is a beam splitter. And if I choose a velocity to ramp through this avoided crossing, not too fast and not too slow, I can actually split the qubit state coherently into ground and excited state. It's now, the qubit state has different energies. It accumulates a relative phase in this gray region. And then when I pull the qubit state back through the avoided crossing a second time, interferes with itself. Itself interferes quantum mechanically, and that will dictate, that phase will dictate whether it returns to the ground state, the excited state, or some combination of the two. And based on that, we get something called Stuckelberg oscillations, which is the interference fringes due to this phase, and that's what these oscillations are. Okay. So we wanted to use this to do coherent scattering, and so it's this Landau-Zener interference, as I just showed, and you can view it as the energy as a function of time, the energy separation. And here is one beam splitter or avoided crossing. Here at time, we hit the avoided crossing a second time. So in the usual case of coherent backscattering, we have a, say, a condensed matter system with many scatterers. And this leads to some kind of chaotic behavior depending on where they're located. In the driven qubit, it's a single scatterer, but we can traverse it many times depending on the waveform and how we go through the avoided crossing. And this is, in a sense, it's a deterministic behavior in the sense that we are defining the waveform, but then we can define many different waveforms and bring in a notion of stochasticity. So how does it work, or how do we break time reversal symmetry? So in a driven system, time reversal symmetry is imposed by the waveform. And so an asymmetric waveform will break that time reversal symmetry. In this experiment, we decided to implement asymmetry by using biharmonic driving. So two sinusoids with different amplitudes, and with one of them we add a phase alpha, and that alpha is going to be this asymmetry parameter that I discussed. And so depending on the values of alpha, you see that you can introduce asymmetry into the waveform and change something from what looks like a symmetric pattern in time to a driving where now this is asymmetric in time. So that's the concept. And the way it works is that if we start, say, at this point number 1 and we drive over in this direction, we're on the lower part of this waveform, so we just go through the avoided crossing one time. Same thing with 2. But if we start on the other side of the avoided crossing, we now pass through the avoided crossing several times. And depending on this value of alpha, we'll accumulate different amounts of phases in these shaded regions. Okay. And so this is the last slide. This is the result of this experiment. So what we see here is the bias value of the qubit on this side. That's the flux bias. And on this axis is the asymmetry parameter. And then these are the essentially interferences that we see. And there's clearly structure here, but it shouldn't be that you recognize this as something you once saw before. I mean, it's really, this, as a function of this asymmetry parameter, this is what we observed. And what's being plotted in the color scale is the transition rate from the ground to the excited state. And that's the analog of conductance. The transition rate, how quickly did I drive this from ground to excited state? And if we look at the first order statistic, the average value of that transition rate, we find that it's independent of the asymmetry parameter. And what that means, and I can answer questions later in the interest of time, is that we don't see weak localization in this system. And it's likely due to the fact that we have a single or only a few scatterers, and we're enhancing both the forward and the backward scattering. But what we do find is if we look at the second order statistic, or the standard deviation, square root of that, we do find a very sharp peak at 0 asymmetry, and it decreases outside of that. And this looks a lot like, and has an analog to universal conductance fluctuations in a condensed matter system. And so with that, let me summarize. Okay, I think we all know that quantum computing is transitioning from a laboratory curiosity to something that's really technically real. And we believe that the next step is a 10 to 100 qubit testbed for qubit simulations and emulations. And we, in parallel with that, can do prototype logical qubit demonstrations. And at Lincoln, we're working on superconducting qubits and trapped ions with a focus on extensibility, high performance electronics and photonics and 3D integration. And let me flash up our team here to recognize them. Thank you.
While Monica is setting up, we have maybe time for a question or two.
So that's the indium bump bonds, we've put 4,000 or so in series. And at this point, we can bound it to the DC resistance to it's less than 100 nanoohms. We're now going to do a transition temperature measurement to show that it's actually superconducting. We've also put the bumps into resonators to see what the AC response is. And there, we see a higher resistance. And so we're trying to understand why that is. It's typically maybe 100 microohms per bump. And so, yeah, that's right. That's at around 5 gigahertz. So we don't quite understand why that is yet, but that's what it is.
One more question from Lynn.
Yes, right. Near future. Yeah, I'm not sure. I think that we have ideas to do that, but the temperature differences are quite large. Right now, we're operating the ion trap at 4 Kelvin. Of course, the qubits are at millikelvin temperatures, and having a microwave to optical conversion might be one way around that. Yeah, the voltages that we need to drive to control the ion trap itself, those are actually quite large.
Okay, let's thank William for his wonderful talk. Our next speaker is Monica Schleier-Smith, and she's going to talk about echoes of entanglement. So that sounds quite exciting. And